In this section, we're going to talk about one possible solution to the remove at method. Before we start writing any code, I want to identify two very easy to find edge cases that we're going to need to handle. So the first edge case I want to think about is the case in which we have no nodes in our chain at all. So if we have no nodes, then we should immediately return. And remember, we can check to see whether or not we have any nodes by looking at the this.head property. Now the second solution, or the second edge case that I want to talk about here, is the case in which we are trying to delete the first node. So the possible solution I laid out at the end of the last video was to reuse that getAt method. So we can reuse getAt to try to find the node at the index one less than the one that we're trying to remove. So in this case, we had said, oh yeah, let's try to remove the element at index 1. So that would have been this one right here. So we could have used getAt to find the node right before it. So what happens, however, here's the edge case, what happens if we are trying to remove the node at index 0? In this case, there is no previous node. So there's nothing over here. So we need to make sure that we handle the case in which we are trying to delete the very first element as well. So those are two corner cases that I can immediately think of. There is one more corner case, but it's only going to kind of become obvious later on through our solution. So we'll come back to this diagram in just a little bit and talk about what that third corner case is. All right, so back inside my index.js file, I'm going to add on my remove at method, which is going to get called with some argument index. So this is going to be the index of the element that we want to get rid of. So the first thing we'll do is check to see if our list is empty. So we'll say if there is no head element, then just immediately return. Let's check our tests and see how we're doing over here. So it looks like remove at is now passing the first test here, which is to not crash on an empty list. You'll notice that there's another method here that says make sure that you don't crash on an index out of bounds, and it looks like we are passing that one as well, but it's only saying it doesn't crash. Right now we're not really doing anything at all, so that test might be passing kind of erroneously at this point. Now the next case that we'll take care of is the case in which we are trying to remove the head element. So if index is equal to 0, if we're trying to remove the very first element, the element at index of 0, then we don't want to try to use any fancy algorithm here or anything like that. We're going to repair the chain, or we're going to update the chain very manually in this case. So we'll say this.head will be this.head.next. So in other words, rather than pointing at this first element right here, point at the second one in the chain. And that effectively removes the first element. And remember, this will work even if the list only has one element inside of it. If there was only one element here, the next value would have been null. So if we point head at null, that still works the way we expect it to. Because if we remove the only element, well, then our list is empty and head should be pointing at null. All right. So if we meet this if statement right here, we need to also make sure that we immediately return from the function as well, because we don't want to execute any other logic. Now here's where things start to get a little bit more interesting. So here's where we're going to reuse our getAt method. We're going to reuse getAt to attempt to find the previous node, or the one right before the one that we are trying to remove. So if we are trying to remove the index at 1, I want to get the element at index 0. So we'll say const previous is this.getAt index -1. So notice the very clear choice of variables here. We're saying this is going to be called previous just to make sure that it's very clear to any reader that we are finding the previous, or the node occurring right before the one that we're trying to remove. One thing I would really encourage you not to do is to call this something like node, because then the meaning is kind of lost and we immediately have to ask the question, okay, is this the node we're trying to delete, or is this the node right before the one we're trying to delete? And there's really no ambiguity there if we call it previous or something similar to it. All right, so now here's where we start to run into some other corner cases. The first thing that I want to do is to kind of put together the direct solution, and then we'll worry about the corner case. We'll see the corner case, or the edge case here, start to fail on our test in just a moment, but let's first try to get our stuff working. So if we found the previous node, so if we found this one right here, we need to make sure that we update the next property to look into the future. So I want to make sure that previous.next looks at previous.next, which would be this one, .next, which would be this one. So that's going to be a little bit weird looking. We're going to say previous.next. So the next node we should be looking at is the current next.next. So this is a confusing line of code. Just one more time, let's look at the diagram very quickly. So at present, when we first run that line of code, previous.next is looking at blue. The one that we want to look at will be previous.next.next. So that's previous.next.next. And we're going to assign that to previous.next. So that's what's going to leapfrog blue right here and make sure that we point directly at red. All right, let's save this and see exactly what happens, because I'm not entirely sure that we're going to get the correct result in all cases. So if I flip back over, here's remove at, and you can very quickly see that remove at is crashing on an index that is out of bounds. So here's the third corner case. This is the case in which we accidentally call remove at on an index that is greater than the total number of nodes that we have inside of our linked list. So this would be the case, for example, in which we try to call remove at with an index of 12 when we only have 3 elements here. So this is going to be a solution, or something that we can probably figure out a solution to pretty easily. Remember that the getAt method is wired up to return null if we try to find some element that doesn't actually exist inside of our linked list. So we can exploit that to put in a little bit of a check to make sure that we are actually retrieving a valid previous element right here. So right before we try to update previous.next, we'll say if previous does not exist, then just return. So this right here would handle the case in which we just attempted to ask for an index that was out of the bounds of our linked list. So let's see how our tests are doing now. Well, it looks like that test is still failing. So what situation could this be failing in? Well, this is a very, very corner case, but let's look back at our diagram and try to think about one more corner case in which this might fail. Okay, so back at this diagram right here, let's imagine that our linked list has 3 nodes, exactly as it does right here. And then let's say maybe we try to call remove at with an index of 3. So what would happen here? Remember, index 0, index 1, index 2. Index 3 is null, so there's nothing here. When we call getAt with index -1, that would retrieve the previous element, which would be red. So in this case, when we called getAt, it did successfully return an element. Something does exist here. However, the next element in the chain is null. So when we try to call previous.next, this returns null. And when we then call .next on that with this extra .next on here, we are trying to read the property .next of undefined. And that's where the error is coming from. So this is a super edge case in which we are trying to remove the index at the one, or the index is essentially one larger than the total size of our linked list right here. So a huge edge case just to be aware of. So to catch this situation, we can add on another statement or another condition to our if statement right here to make sure that we have a valid previous node to work on. So we'll say if previous was not found, or if previous does not have a next node. So if we were not able to retrieve the node at the given index, or if that node is actually the last one, then hey, you know what? We need to return. We can't possibly remove the node at the provided index. So let's save this and now see how we're doing. So back over at the terminal. Yep, looks like we got all tests passing. Okay, so this was, a method where at first glance it seemed very similar to some of the other ones that we wrote, but when you really start to think about it, there are several edge cases that we had to consider. So we did come to a solution, which is fantastic. Now there's just one more method that we're going to work on that is kind of a repeat of all the ones that we've already done. So let's tackle that one in the next section. It's going to be insert at. So we'll tackle that in the next section, and then we'll move on to 2 additional possible steps here that are a little bit more advanced. So quick break, and I'll see you in just a moment.